This presentation is detecting ADS-B replay cyber attacks in the National Airspace System. And I'll be running an ongoing demonstration as we progress through. And it's in these three terminal windows. The first one is a list of aircraft that's constantly updated that are in my vicinity. The second one is digital signal processing software to read that information from the transponder and then provide that on shared memory. And then the third one reads the shared memory and does the replay attack checks. So let's go ahead and get started. Avionics equipment is essential for safe flight operations and is part of the networks that share data with the flight crews, other aircraft, and air traffic control system. The Government Accountability Office, also known as the GAO, presented a report to the U.S. Congress on the cybersecurity risks to the national airspace system from vulnerabilities in avionics systems. In its report, the GAO found that the FAA has not fully assessed the avionics risks in the national airspace, and that one of those systems, Automatic Dependent Surveillance Broadcast, or ADS-B, posed significant risks. So this presentation will report on the nature of the information vulnerabilities posed by the ADS-B avionics system. It'll further detail the setup of a software-defined radio, or SDR system, to receive ADS-B transmissions from aircraft and insert them into a data store for analysis of the factors that affect replay cyber attacks on ADS-B. A detection system is developed that addresses the factors affecting ADS-B attacks, and then our results are presented. So, compared with current surveillance radars used in air traffic control, ADS-B has an easier and lower cost implementation and produces highly accurate data. Because ADS-B ground stations can be installed in any location, and I just installed a ground station in my office to record this, they don't have the problem of uncovered spots present in the current system. And that's where, in the current system has problems, is where those locations where ground radar cannot be installed. So even more, there's better location accuracy of ADS-B, and that permits smaller aircraft separations, and that results in higher capacity. Now, an aircraft equipped with ADS-B receives information from other aircraft from ground control and position information from onboard receivers. An aircraft equipped with ADS-B out sends position and velocity data from the aircraft systems through the Mode S transponder. So there's an ADS-B Mode S transponder on board that then sends the message traffic to air traffic control and other aircraft. Current radar surveillance technologies are having difficulty meeting the increased needs of air traffic management. ADS-B is an open architecture that broadcasts its messages in a simple format, and so it becomes an opportunity for hackers. ADS-B is vulnerable to eavesdropping, jamming, modification, injection, and replay or playback attacks. An ADS-B system cannot identify authorized users from unauthorized, and it's therefore vulnerable to spoofing attacks. So ADS-B transponders broadcast messages using the radar Mode S protocol. Mode S was a successor to the original ATC radar contact system. Mode S addressed overloading that occurred in the radar beacon systems used in air traffic control. Mode S includes selective interrogation that can be directed to a single aircraft rather than to all aircraft. Now, Mode S-ES is an extension of Mode S in which packet length was increased from 56 bits to 112. And that allowed for inclusion of GNSS or GPS information in the messages. Mode S-ES is also known as 1090 ES, and it's the standard data link for ADS-B. ADS-B transmits 120 microsecond messages that have a data block of 112 bits that use 112 of those microseconds, and the other 8 microseconds are for a synchronization preamble. The Mode S broadcast message has two formats, the 56-bit short message and then the 112-bit extended message used by ADS-B. The fields in the ADS-B message structure are shown here. You have an 8-second preamble for syncing. The first 5 bits are the format encoding the message itself, and there are several different data link or download downlink formats. And 17 is the one that's for ADS-B. The second 3 bits is the transponder capability, and then the third 24 bits is a unique aircraft identifier known as its ICAO ID. The next 56 bits refer to field data such as call sign, position, velocity, and so on. And then the last 24 bits are a parity code. ADS-B has vulnerabilities. It is based on a simple protocol that is unencrypted and unauthenticated. Because of this, there are concerns about ADS-B vulnerability to jamming and spoofing. The types of potential cyber attacks on the ADS-B system are shown here. A jamming is aimed at the receiver system and consists of a high-powered RF signal that's broadcast at 1090 megahertz, the same frequency used by ADS-B to transmit its messages. The purpose of jamming is to disable the 1090 megahertz signals sent by the ADS-B system. Spoofing, on the other hand, attempts to introduce false messages into the 1090 megahertz traffic so that ADS-B in systems, so you have an ADS-B out that sends the messages, and then you have an ADS-B in system that receives them. So the spoofing is designed so that ADS-B in systems process incorrect information. This can result in spurious positions for actual aircraft and the introduction of fictitious aircraft. Both of these can result in failure of traffic management by flooding the airspace with ghosts or falsely representing aircraft flight paths as being on a collision course. Spoofing attacks can be executed with inexpensive software-defined radio equipment and a PC. The purpose of ADS-B spoofing is to disrupt airspace surveillance or to hijack planes or drones. Spoofing poses more risk to the system than jamming because the target system that's unaware it's under attack cannot raise an alert to the rest of the system. A replay attack is a form of ADS-B spoofing where authentic ADS-B messages are recorded and then later retransmitted. Different approaches to detecting spoofing have been proposed. These include cryptographic message, signal separation, position, velocity, time verification, and Doppler shift analysis. There are three types of attack: ghost aircraft injection, aircraft spoofing, and IQ data replay. IQ is in phase and quadrature, and these are two signals that have the same frequency but differ in phase by 90 degrees. Some attacks attempt to introduce a ghost airplane into the air traffic control space. This can be from a ground-based software-defined radio, either using a replay attack in which previously recorded messages are inserted into the airspace, or from a new message that's constructed by the hacker that introduces a ghost plane. Another method of attack is from the air, aircraft spoofing, and that uses ADS-B transponder with a modified ICAO ID, which is the unique transponder identifier assigned by the ICAO. There are proposals for data mining, a data mining approach to detect an ADS-B spoofing attack. Valid ADS-B messages are used to train a neural network, which is then used to discover irregularities in incoming message sequences. The model then detects that those changes are not legitimate. A risk in such an approach is of overfitting the data and of catastrophic forgetting. In addition, a replay attack is going to have valid position and velocity information because it is based on real message traffic. Most of the other detection approaches for ADS-B spoofing in the literature were based on electronic methods. In our method, in contrast to most of the others, we use a data-driven approach. The contribution of this research is using a classic data analytic approach, cosine similarity, to do real-time detection using message data. So our approach is to compare messages coming from an ADS-B transponder with a database of saved traffic to find an indication that the spatial information is identical to one broadcast in the past, a replay attack. The next few slides I go through will explain the methodology used to integrate an ADS-B system with a microcomputer to do a detailed analysis. Also explained is the structure of the database, loading ADS-B data into the database, and the algorithm for determining if an input stream of live messages represents a replay attack. We used a shared memory parallelism so the detection system would be scalable and able to keep up with incoming data stream with increasing loads. The approach to parallelism is shown here, and the author's laptop computer has 8 logical processors, and the design is able to spread the calculation load over the multiple processors. Until recently, radio signals were decoded and processed by analog electronic circuitry. As microcomputers became more powerful, the mathematics to process radio signals can be performed quickly enough by software. In addition, Linux engineers developed drivers that transformed the RTL2832U chip into a wideband general purpose radio receiver. The methodology in this paper uses an RTL2832U based dongle that attaches to a microcomputer via the USB interface. A coax cable connects the receiver to a single pole antenna. Software drivers are installed that enable the operating system to communicate with the radio receiver as shown here. And again, ADS-B messages are transmitted at 1090 megahertz. An analog to digital converter on the RTL2832 chip samples the radio waves and digitizes the samples. The resulting IQ, in-phase and quadrature data is made available by the USB controller on the RTL2832. The software digital signal processing on the microcomputer that can then at that point process the IQ data as appropriate. The approach used with the RTL2832 provides the authors with either IQ data or hexadecimal messages processed from the IQ data. We use the processed hexadecimal messages. Cosine similarity is a measurement calculation to tell us how similar two data sets are to each other. If the calculation results in 1, then the two data sets are identical, while at 0, they have nothing in common. It is widely used to compare two different documents to gauge the similarity of those documents. In our case, the single 56-bit hexadecimal message, and that's essentially a 14-character word since there's 4 bits per hex character, is our word. So the 56-bit hex message is our word, and the set of messages for a specific aircraft is our document. We will get incoming messages for every aircraft currently in the traffic space, and we want to compare the set of messages from an aircraft with what is in store. If we get a match, we collect the message set from the store for the stored aircraft that has that message map, and then we compare that message set with the incoming message set that provided us with the message that had a match in our database. If a cosine is above a threshold of similarity, then we flag the culprit incoming aircraft message and say that that aircraft is a possible replay attack. A simple approach for detection would be to index the database table and then just look for a match. That won't work, however, if there are naturally occurring duplicates, because the match may end up being the result of a naturally occurring duplicate. And that's what we've discovered, is that there are naturally occurring duplicates. So the first analytic query is to find out if there is a duplicate message stored in the data, which would be that we look up the message in the database table. Finding it isn't only means that we go on to the next step. It is an assurance that it's a replay attack. So if there is a match, then we do the cosine similarity comparison. We grab all the messages for that aircraft in the data store and compare it with the message set for the incoming aircraft. So naturally occurring duplicates were discovered in the analysis. With duplicate messages naturally occurring both within and between aircraft, there will be database matches with incoming traffic, even if it isn't a replay attack. So to find the threshold resulting from legitimate duplicates, The 13,481 aircraft message sets stored in the database were compared with each other. In other words, we calculated the cosine similarity between each of those. We found that 99.99% of the calculated cosine scores between aircraft message set vectors sharing duplicate message sets were below the cosine similarity of 0.07. So we selected this as our threshold for identifying a replay attack when analyzing incoming messages. And the results of this analysis are shown on our graph on this slide. Now, in our initial configuration, the detection process could not keep up with the pace of the incoming traffic from the radio transponder. Preliminary tests were done on a prototype of the application to determine which configurations provided performance improvements. A multi-threaded version of the application was prepared. We used Python as our programming language, and the multi-threaded version proved to add no value to the performance. We looked at the computer system performance monitoring indicators, and there were no indications of CPU or I/O pressure in the application. So to discover the lag in the detection processing in relation to the feed of the transponder messages, we put timers in our Python code. Database calls in the program resulted in significant delays, up to 200 milliseconds. Another test was run to determine if an in-memory database provided performance improvement, and a comparison of the times with a database on disk and database in memory likewise found there was no improvement in performance with an in-memory database. Our explanation for these outcomes is that the context switch when calling the database is what resulted in the delay. To test this hypothesis, we use dictionaries, which are key value data stores native to the Python programming language, and they were preloaded with data from the database and used in the detection algorithm instead of database calls. So with this approach, we made no outside calls to the database system. With this change, the detection program was able to provide real-time processing of the incoming message feed and was able to keep up with the traffic. So the detection program performed cosine similarity on various replay attack scenarios. In validation testing, it was able to detect all the invalid ICAO ID for the all three tests, the single, the swarm, and the spaced. And the test that I'm running in this ongoing demonstration is a spaced attack. I feed I'm into the stream of data I get from my radio transponder. I will feed intentional replay attacks from a disk file periodically, and I do it at various times. And so this is the spaced attack. The tests were run on a laptop computer with 32 GB of RAM and 4 cores with 2 threads per core, yielding 8 logical processors. The multiple processors ran in parallel, and this did not stress the CPU, memory, or disk capability. A principal issue in using any data-driven approach is the amount of data that needs to be stored and present. As to scalability, our findings show that a week's worth of data can readily be handled by a single logical processor and 2.5 gigabytes of memory. Current servers can provide 896 logical processors and 6 terabytes of memory. The need for this detection system are basically 1 times 52, one per week, times 52 weeks per year times 10 years, or that's going to be about 520 processors, the way we have it set up, with each processor dedicated to a data set of stored data for 1 week. And likewise for memory, 2.5 GB times 52 times 10, or 1,300 GB, or 1.3 terabytes of memory to handle a decade's worth of data. Our parallel processing architecture was tested with multiple processes running smoothly while working on the load from the transponder dongle. So detecting the presence of a replay attack is the first step in mitigating it. The GAO notes that once ADS-B spoofing is detected, air traffic controllers can begin actions to work with the systems involved to resolve the situation through controller-pilot communications. In addition, the ICAO ID of the aircraft with the that is involved in the replay attack could be sent to the surveillance radars that'll still be present to some extent in the next-gen air traffic control system, and those can be then employed to triangulate a fix on the location of the culprit. So in conclusion, by applying a classic data science method, replay attacks can be detected real time, and since the approach does not involve modification of the existing ADS-B protocol, it's a practical mitigation to mitigate replay attack vulnerabilities in the national airspace system. Another key implication is that, based on the findings, a key implication for air traffic management is that a decade's worth of ADS-B data and detection for a particular ground station can fit on servers that are currently available. Thank you.